are these strings there? The theory predicts that these fundamental length scales of strings are so small that we would need a particle accelerator about the size of the solar system in order to smash atoms together and directly see those strings, which unfortunately we do not have access to those types of energy scales yet.
Just to affirm what is implicit in your statement, the larger the particle accelerator, the faster you can speed the particles so that when they collide, there's much more energy in that collision. You'll probe regimes that previous accelerators could not.
That's right.
Okay, and so you just scale up what we got going now, and you need something the size of the solar system to get to these energies.
Right, which doesn't seem very viable.
No, it's not. Gosh, so what's plan B?
Before I answer that, let me just throw one thing out there about string theory that I think is important to say. So if you ask about quantum mechanical point particles, and you say, what kind of spaces could they move through? It turns out that quantum field theory or quantum mechanics can be formulated in any type of space. So they can move through basically any background that you choose, any configuration in space and time. But if you ask the same question for these little one-dimensional strings, if you say, where can a quantum mechanical string move? It turns out that the only spaces that they're allowed to move in and do their thing of vibrating in different ways and being different particles, the only space they can do that in are spaces that obey Einstein's equations of general relativity.
That sounds good.
Wow.
Yeah, so you actually get gravity for free in this formulation of quantum mechanical strings. So we sometimes say that quantum gravity is consistent and also compulsory in string theory because it's being, you're forced on you by the equations that the strings can satisfy.
So that's a good feeling then, because it means something is talking to something else in the formulation.
Right.
That was not crowbarred in to begin with.
That's right. So it's sort of being handed to you. And that fact is, I think, something that early in the development of string theory got a lot of people excited. Unfortunately, like many good things, things come with a catch. And the catch in string theory is that this beautiful formulation I just described of, you can describe all the particle physics by one little extended object, you get gravity for free, only seems to work if the universe that this happens in has more than 3 spatial dimensions and 1 time-length dimension that we seem to see in our universe.
So you need extra dimensions because right now we live in 4 dimensions, which is 3 spatial plus time. You need more dimensions in order to make this thing work, but we don't have access to more dimensions, so we can't really say for sure.
Well, it seems like a really big intellectual leap, right? We're pretty happy with our 3 dimensions of space and 1 dimension of time. So the first pass is could this at all, is this just a deal breaker, right? Is there any way that this could be consistent with what we've already observed about the universe? And as you were just alluding to, right, the question is, could such extra dimensions exist? And if so, how would we try and probe whether that's the case? The requirement that we can see right off the bat about these extra dimensions is if they were to exist, they can't be the same size as the rest of the dimensions that we see in our universe. So if we look around, we can see that, we have very large spatial extent for, front, back, side to side, up and down, and of course time. But if there were these other directions, they would have to be really, really small compared to the rest of our universe. And the analog for that is, if you imagine looking at an extended object like a wire from really far away, it just looks one-dimensional. It just looks like it has a length. But if you were able to get really close to that wire, you'd see that it also has something like a thickness, a radial direction. And so that extra direction is what's called compact, meaning that it's very small compared to, say, the length of the wire. So one thing that we do know is that if this had any chance of working, these extra dimensions would have to be compact and very small compared to the rest of our universe.
Okay, you're freaking me out right now because, I'm just going to say it. So I was down in Costa Rica doing ayahuasca for a week. And in that time, I had an experience where I met these beings who told me about dimensions that existed inside of our dimension. So they were alongside of, yet inside of the dimension that we live in. And I can only think that maybe that was a presupposed pre-planted post-hypnotic suggestion because I have actually read about string theory. Because if it's not,
or Laura, what drugs have you been taking to get your?
And my follow-up question is, what did you do?
That's right.
I hear the question. Yeah.
Is it possible to have a compactified time dimension as well? Or is all of the models only stuck with one time dimension?
Oh, wow. I've never even considered that.
Yeah, imagine 2 dimensions of time.
Wow. Holy crap. Go ahead. Yes.
So the problem with 2 time dimensional theories and compact time dimensions in general is that it's very hard to maintain causality in such theories. So if you have a time direction that can loop back on itself, it's possible to have the whole go back in time and shoot your grandpa situation hitting you pretty hard. So to maintain consistent theories with multiple time directions or compact time directions, I'm not going to say it's impossible, but most people don't consider that a very viable way forward.
You would have to discard causality altogether in order to do that?
I think in general, the claim would be it would violate causality in such theories. So there may be some creative ways to get around that, but generically, I think that's true.
By the way, we have a Stephen Hawking on one of our earlier episodes. You can find it in our archives. We went to University of Cambridge and chilled with him for a bit. Tell me, he proposed a time travel conjecture, something like that. So tell us what that was. And does that save us from this?
There are a number of conjectures, say, in the theory of gravity that say that causality is an important structure. So that in general, one would not expect that consistent theories of gravity or indeed quantum mechanics should allow such.
You just can't get it to work. Okay.
Yeah.
That's fine. That removes many movies in the repertoire where you got to go back and change the past.
Exactly.
Like Terminator.
All the Terminator is done. Right. Forget about it. We look back on the past, but we look forward to many futures. So the idea of being able to look back and say, at this particular point, all those many futures still exist. If I could get back to that point, then I could change it to one of these other tracks, which, I mean, it's a great fantasy and it makes sense to have that fantasy. But what you're saying is it's a stupid fantasy because it ain't never going to happen.
Well, I would say, never say never in science. You got to be careful, but certainly it's not something that most people have a good idea how to make work in a consistent way.
And that's why I'm not a scientist.
And just consider to say never, you said never.
You just said never.
You can't say never
without saying never.
Hey, Star Talk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that on Spotify, Apple Podcast, and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic.
Before we sort of pivot to the whole thing of phenomenology, because I want to know, it's a big word with a lot of syllables. I've heard it invoked before, especially in particle physics. But before we step there, I just want to understand, how will you ever test string theory? And we know in advance that you have naysayers out there, physicists among them, who are saying you're diverting time, resources, graduate students, faculty positions to something that doesn't even classify as a legitimate scientific theory or hypothesis, because you need to be able to test it. Without the test, go home. So let me hear your response to that.
Absolutely. I think that's a really fair question. For any theoretical framework where you're trying to describe things, if there's a big intellectual leap, right, and for example, extra dimensions is a pretty big leap, you have to justify that with a payoff, right? You have to say, what is the benefit that I'm going to give you in terms of structure and predictions and what you're learning from this theory. So to push back on the, how are we going to test it? Let me observe first that in particle theory in general, the timescales between predicting structure in particle theory and then being able to see it in experiment over the last half century have gone, increased in size considerably. So one example of this is the prediction of the Higgs boson made by Peter Higgs, which took about 50 years from the prediction that this particle should exist to its observation at the LHC.
That means the theorists are just way ahead of the experimentalists. Right. You got some deadbeat experimentalists.
I would not say that at all. I would say that dialogue of theory and experiment is really important, but I'm just pointing out that direct verification by experiment of lots of things is hard. That doesn't mean that one shouldn't do it. It just means that, you have to be deciding what timescales are relevant for that question. For string theory, I would say the problem is a lot worse than it was for something like the prediction of the Higgs boson, because the energy scales are so massive to directly observe strings. So for me personally, I'm interested in trying to decide whether string theory is useful a lot faster than that in the point of view of my career. And I remain very agnostic as to whether that's the case. So
you want to be alive when
I want to be alive when we decide this. And also, if somebody could demonstrate to me right now that string theory was for sure not useful for our universe, I'd choose to work on something else. So what do I think is the sort of most direct way to those types of answers is that in string theory, many types of structure and results in physics are really intercorrelated. So it turns out that in something like the particle physics description of all the particles we know about so far, the standard model of particle physics.
So that's the organization of all the particles that we know in one chart. And you say this interacts with that, and this connects here, and it's a beautiful thing actually when you step back and. It's a triumph. I mean, that happened I'm older than both y'all. That happened in my lifetime. I mean, basically the 1970s.
Wow.
We started assembling a little earlier too, but the full picture was coming together as we found these other particles to flesh it out.
So it's a periodic table of particles.
Okay. All right. An organizing principle.
Yeah.
Very good. Okay. So pick it up there. Sorry.
Quick anecdote from when I was a kid. I got interested in physics, reading books by people like Brian Greene when I was, in my early teens. And I had a little, I'd written down the standard model, on a piece of paper. I made my little zoo of particles, and I carried it around on a piece of paper for a bit as a super, nerdy young person.
Girl geek in the house.
Love it.
Girl geek alert.
Yeah, totally. But I totally agree. It's the zoo of what we know is there. And the point I was going to make in relation to string theory is that in something like the standard model, there's a lot of free numbers. So for example, nothing in that theory tells you what the mass of the electron is or how the quarks couple to each other. Those numbers are just observed in our universe.
When you said free numbers, you mean not predicted.
Correct, not predicted by the structure of the theory. Now, in contrast to that, in string theory, if you found a solution of string theory that produced particle physics like we see in our universe, none of those numbers are free. They're all determined by the configuration of these extra dimensions and the structure of the theory. So it's a huge array of physics that you have to get right all at once. And here I've been talking about particle physics, but you also have to answer questions about cosmology and the large-scale structure and history of the universe. So how are you going to decide if string theory is wrong? I think that it's most likely that we would be able to say that the structures that we see in nature, we can argue that we either can or can't get the right sort of regimes of numbers and effects that we already know are there, much more rapidly than we're going to build an accelerator to see a string.
I love that.
Oh, that's...
Yeah. So what you're saying is, whether or not you can test the dimensionality or the other sort of physicality of string theory, if your theorist can go in the back room and come out and say, I pluck this string this way, it's going to give me an electron, and it's going to give me this mass.
Right.
And it's the only mass that's going to come out of this.
Right, because that's the right number.
It's the right number and the right vibration, and it's going to look like an electron. That's a Nobel Prize right there.
Yeah. It's like the way they do modeling or weather modeling. We have a prediction, and then we run the model on what's already been done. And if we get those numbers, then we can have confidence in the predictive model itself.
That's right. Again, so the idea, as I just articulated it, this has been around for 40 years. This was when people were first formulating string theory, everybody was excited, and they thought we were going to do exactly what you just said. You're going to go around, you're going to look at the solutions of the string theory, you're going to say, boom, here's our universe, here's all these numbers, we just predicted everything, it's great. That hasn't happened, and people are still trying to think about this. So what are some of the big obstacles? One of the issues is that it turns out that when you ask how many different configurations for these extra dimensions can there be, initially the hope was that maybe that was very restricted, maybe there was just a couple. The question of how many could you have? So if you said, what if we just had, say, 2 extra dimensions that obeyed the consistency equations from string theory? Turns out there's a unique answer from the differential equations that tell you what that shape could be. If you ask, is there, what happens if there are 4 extra dimensions? There's a unique answer. And then if you say, what happens if there were 6 extra dimensions, which happens to be the extra dimensions that we think needs to arise to give what we see in nature, turns out there are 500 million configurations and counting that have been found so far.
So it sounds to me like what you guys are saying is we have this instrument, and on the instrument there's a certain amount of notes that are just resident in the instrument. And now we have to figure out one song because all those notes can make however many billions of songs.
We need the one
We
song.
got to find the one song that all those notes can play.
But it also sounds like nature's just messing with us.
Yeah.
It sounds, so this is one of the things that people push back on string theory on, is they say, okay, if all these possible solutions of string theory exist, how is it ever going to be predicted? And, you could just have this big soup of things. And some people have even made that argument. They call it the string landscape, where they say, you could just land anywhere. So what if there's some place in the string landscape that looks like our universe? There's all this other junk. What is the theory actually telling us then? And the argument I would say against that is that in something like quantum field theory, which we already talked about for the standard model, this zoo of all the quarks and leptons that we know in nature, there are an infinite number of quantum field theories that I could write down that aren't our universe. But it doesn't matter because we do know how to write down one that does look like our universe. So string theory is sort of a natural extension of quantum field theory in some ways, and it has a lot of flexibility that may have nothing to do with the physics that we observe in our universe. But the question is, once you zoom in on the parts of that theory that do you learn anything? So, for example, do you find that if you see the particles that we already know, that additional particles must be there, or additional forces? Or can we correlate features in cosmology and the large-scale structure of the universe, like dark energy or dark matter, with particle physics that we know to be true?
I don't want to lessen the significance of how you describe that, but if I understand it, you're saying on this, like you said, this landscape of 500 million possible songs that it could be, and you want the one song that's yours. It's not useful if you find it unless upon finding it, you get other insights about the universe we're in. Because otherwise it's just a just so story. Right? It's the universe is just that, and we explain it with just that, and it doesn't take you any further down the street. Is that a fair way to characterize it?
Yeah, and another thing that people are asking within string theory is, how many possible quantum theories of gravity could there be? So imagine that string theory isn't how our universe works. We know it's a quantum theory of gravity, but it might be too idealized to describe our universe. So in physics, we talk about, pretending that cows are spheres in order to make the math easier.
Just consider a spherical cow.
Oh, God.
We do that all the time.
Okay.
It's just easier.
Our Society of Physics students has a spherical cow T-shirt here for at Virginia Tech.
Yeah, it's a thing.
That's pretty wild.
It's a thing. If you want to maximize the milk production of a cow, start with a spherical cow.
Start with a spherical cow.
Yeah.
Right on. Yeah. I don't want that milk. I don't want milk from a spherical cow. I'm sorry. Yeah, I'm going goat's milk from now on. Yeah.
But yeah, the point I'm making is that maybe string theory isn't, it's just too idealized to describe how quantum gravity works in our universe. But a lot of theorists are questioning, okay, if that's the case, we know this is a quantum theory of gravity. So if you had another one, like the right one that isn't string theory, how could those two theories be related? And there's groups of string theorists who are trying to argue and provide mathematical theorems. For example, someone named Herman Bappe at Harvard has created something called the cobordism conjecture. And what he's positing is that perhaps if you had more than one quantum theory of gravity, they must be connected in some way. Otherwise, you would develop inconsistencies in how you could describe quantum gravity or quantum gravitational effects. So the argument I'm making here is that even if string theory isn't the right one, whatever that might mean, maybe it's connected to the right one. So maybe we still learn structure about how string theory can inform what our universe should look like.
Is this what, not exactly what you just said, but the comprehensive look at all of this, is this what gives rise to the multiverse and infinite number of universes?
That's a different question, but an interesting one.
The answer is no.
The answer is no. Okay.
Maybe we'll say that for
we'll say that for later. Yeah. Okay.
Your specific specialty within string theory is particle phenomenology. And could you just introduce us to that?
Absolutely. So that's the question of whether string theory can produce solutions that look like the particle physics that we see, the standard model, for example, and the interactions of the other fundamental forces that aren't gravity. And so one of the things that I've worked on at various times over my career is trying to ask for the types of solutions that we see in string theory, what characterizes those that would give us things like we see in nature. So again, coming back to this concept of the string landscape, there's a famous number of like possible solutions that you can get for this string landscape, a number of like 10 to the 500, which is unimaginably large, is thrown around.
10 to the 500.
10 to the 500.
That's not a number.
That's not a number. It's crazy.
That's not even a number.
But in that counting of solutions in string theory, so this is, again, something that people say, 10 to the 500, how are you going to learn anything? But all of those 10 to the 500 that people have counted historically, none of them included an electron. Okay? So if you know something about the universe you want to model, you don't care if there's 10 to the 500. Yeah, none of those can possibly give rise to the type of physics we see. So the type of research that I do is trying to correlate what shapes for these extra dimensions, what properties of string theory will narrow the field down to things that are close to our universe.
Okay, so have you gotten there yet? What's What's
the holdup here, Laura?
We're getting better. I mean, in all honesty, we have not delivered on that yet, but we are, I feel like, still making legitimate progress.
Okay, so how about this? Because one of the great redeeming qualities of all scientific discovery, or the search thereof, is even if I don't get to the thing I am trying to find out, along the way, I find out all this other great stuff that now gives us computers and digital cameras and GPS, but I didn't get to what I wanted. So what have you guys contributed that has been your happy accident?
Well, I'm going to say that more tightly.
Say it tighter.
You ready? No, I love that.
Go ahead.
I loved it, but I want to say it another way.
All right, go ahead.
Okay. In your failures, how have you succeeded?
So I think the answer to that is really big, and string theory as a field has really expanded to huge different numbers of subfields and researchers who do really different things. So there are many different answers to that question I could percolating in the back of my mind. One is the discovery of the holographic principle, which says that phenomena like gravity are very deeply related to things called gauge theories, which again describe the interactions of particles and charges, that these things can be related in different dimensions of spaces. So the statement is that gravitational theories can be related to gauge theories that live on the quote boundary of that space. Things like the holographic principle are an extremely deep bit of structure that says that gauge theories and particle physics and gravity are not as different as we thought they were. That's a really profound, I would say, observation that has arisen in string theory.
So the simplest example that I've heard of the holographic principle is the surface of the event horizon of a black hole.
Okay.
And correct me if I'm wrong here. So you fall through, the surface has a memory of everything that passed through.
Interesting.
And so you can think of the information content of the surface as the full understanding of anything.
Everything that's inside.
That's inside.
Because there's no loss of information because it's all retained on the surface.
There. And so that inside the black hole, and if we are inside a black hole of our universe, because we have a horizon, which you can analogize to an event horizon, then we would be the holographic projections of that. So is this a fair, did I capture that correctly?
I think
wow.
Yeah.
Okay, given that, I've yet to heard a physicist rebut that. So is there general agreement that that's probably real?
I mean, in an idealized sense, yes. How much that, pertains, what you learn from that in our universe, I think, is still up for grabs. And this is, again, something people are thinking about very actively. Other analogies that I would give for, useful stuff that's come out of string theory is relationships, again, between things like particle physics and cosmology. So, the study of, dark energy, dark matter, descriptions of inflation, those things being related to, how particle physics realizes those, and also structure in mathematics. So there are a lot of new fields of mathematics that were sparked due to that dialogue between mathematicians and physicists that arose through string theory and these shapes of extra dimensions.
So that's good. So you're exciting mathematicians.
Right.
Yes.
And then they reached out and wanted some of you in their department, right?
Sometimes, yeah. And I think, it's a very much a mutual relationship.
Which is why you're taking a job away from another professor.
So as one example of this, there's something called the Minimal Model Program in geometry, which tries to classify basically all these higher dimensional complex shapes, like all of them. Can you write down compact geometries in any number of dimensions and characterize all their properties and come up with sort of a zoo of every possible geometry?
Wait, we get this is your other specialty,
right?
Algebraic geometry.
That's right.
And was that a spin-off of the rest of these interests? Is that?
No, it's very much tied to it. So the question of trying to produce particle physics from string theory, that's a particle physics question, but the actual computation you have to do really rests on the properties of these compact extra dimensions. So you have to do a ton of geometry to extract the numbers that you want, like the mass of the electron and the coupling of the quarks. So it's sort of intrinsically interdisciplinary in that sense.
Wow.
So I want to hear more about this geometry.
That's crazy.
So here's something that is so simple and low dimensional. So don't laugh at me, but I want you to take this to your level. I was talking with a topologist, algebraic, or one of these math folk, and we were talking about knots.
Okay.
Just knots.
All right.
And you take a string and tie a knot in it, and it's a knot.
It's a square knot.
Or whatever your knot is.
Whatever knot.
Okay, whatever's your knot. And then we're in 3 dimensions here. So a one-dimensional string can make a knot. I said, what's that in 4 spatial dimensions? He said, you can't tie a knot in 4 dimensions. You would just lift it up and it would just unravel. So that just messed with me. And then I thought, let's take away a dimension. Let's go to 2 dimensions. Okay. 2 dimensions. And if you have 2-dimensional people in a flat surface, if you take a rope and just loop it on itself, they cannot undo that. That is an unsolvable knot to them because they can't pass it back over itself to come around.
Right.
All right. But I, in 3 dimensions, just pick it up and it's gone.
Right.
So I couldn't sleep that night. And then I wondered to myself, what is going on in the mind of someone who's imagining all of this in even higher dimensions than that?
What kind of drugs are you hiding? Come on, Laura, don't hold out on me. I shared my ayahuasca. Give us the real dope.
You never told us that ayahuasca high dimensionality person talked to you.
Well, you know what? I have. You guys are the first to know, to be honest, because it was so freaky. It freaked me out, and I never talked about it. But then when she said
it was a string theorist of the future.
Exactly.
Said, you are our savior.
I was the Neo of string theory.
Neo. Yeah. What is the Matrix, Neo? So please tell us.
So I really like the knot analogy. Let me give another one that's sort of more directly related to the kind of stuff I do. So we talked about Einstein's theory of gravity. You could ask, imagine that the entire universe was 2-dimensional, right? Could you have curvature that could lead to like gravitational-like theories in 2 dimensions? And it turns out there's only one number that you get to specify. And it's basically, if you imagine like the surface of a sphere, it's whether it's, positively curved or negatively curved, like a saddle. That's it. And so you can't have dynamical gravity in 2 dimensions. Likewise, the form gravitation takes will change as you go up in dimension. So absolutely, this question of what can you knot and unknot, what can you use to describe how space and time might curve, all of that changes with different dimensions.
Yeah, so you have to get your brain up in that.
I'm telling you right now, I need a nap just from this conversation.
But the cop-out thing here is all the higher dimensions are all compacted, so I don't have to think about or worry about it. I'll never see them, right? How impactful are the compacted dimensions if you're trying to manifest gravity in higher dimensions? Does gravity care if it's compacted or not? Does it just care about the dimensionality?
It does. It does care if it's compact. It cares about the compactness. It cares about the shape of those extra dimensions. And indeed, we believe in string theory that those extra dimensions have to still obey Einstein's equations. So they still have to be consistent gravity in those extra dimensions.
Suppose we lived in 8 dimensions and he came up with general relativity in 8 dimensions.
Right.
Who are you to say his 3 + 1 dimensional thing that higher dimensions have to obey that? He did that in this measly 3 + 1 dimensional world. You can't put commandments on higher dimensions. They are superior to us in every way, and you know it.
Yes, I hate to say it, but higher dimensions look down on us.
That's good.
I'm sorry, I had to do
that's a T-shirt right there.
It is. That is a good T-shirt.
Man.
So I actually torture my undergraduate students in my class on Einstein's theory because Einstein's theory can be actually formulated in any number of dimensions very easily. So there's actually nothing special about 4. So frequently for my students, I'll say, imagine that this was in 6 dimensions or 10 dimensions or,
She said it can be formulated easily, but she didn't say what she meant by easily.
Very relative statement there. But one thing that isn't easy, and this is actually related to why it's hard, again, to really bring string theory to its full fruition, is that when you do Einstein's theory in higher dimensions, the equations you have to solve are nastier. So humans are not really good at nonlinear differential equations, and they are especially not good when they go into high numbers of variables and high numbers of dimensions.
So isn't that something? Okay, so why don't you just get a math fluent AI bot to do this? I mean, that's the whole point of. I mean,
yeah, exactly.
It's hard for you, but give it to an AI.
Yeah.
So one of the things that we've had to try and do in string theory to extract some of these predictions is actually solve Einstein's equations for these extra compact dimensions. And we don't know any analytic solutions for how that means, exact solutions you could write down on a piece of paper for Einstein's theory for the 6 dimensions that we would need for these string compactifications, they're called.
In science, you can solve a problem analytically with an equation, say there's the answer, and some you can't, and you have to actually run the experiment or increment a model and see the results each time just to see where it goes.
Right.
And so that's ugly. We hate those, but we kind of recognize that that's like in chaos theory. You have to sort of calculate it out.
Right.
You can't just write down the solution. So if you're saying you can't in principle, or it's just too laborious?
Just not known how to do it yet. So in general, solving Einstein's equations in any number of dimensions, for any system is hard because they're nonlinear. So what that means is that the gravitational theory is actually back reacting or talking to itself. So the fact that you have gravitons, the quantum mechanical description of gravity in the space, that can create more gravity. So this is really wild in terms of the differential equations because normally you could say, I find one solution to the theory and I find another, and I can just add them together and still get a solution. But in general relativity, that doesn't work. You can't add 2 solutions and get another solution. You have to start over every time.
So when we model, we do this in astrophysics all the time. There's stuff that's just too complicated, but I know at any instant what's supposed to happen, and then I just load that up. But what you're doing is you're calculating with these differential equations, these equations that you can calculate at every time step, and it's following you on the time step.
Right.
All right, but you can't just solve out the whole shebang. So.
Gotcha.
All right. So tell me again why you can't use AI.
So we can actually, and that's a fun topic. So I was involved for a number of years with numeric simulations like you're describing, where you use a computer to try and solve the equations that you can't otherwise. And historically, in order to do those computations, we had to put them on supercomputer clusters and wait for months to get results. But now actually, with the advent of AI, this is something that my collaborators and I have worked on.
And now you just do it on your iPhone.
Now we can actually do it on a laptop. So we've started using machine learning algorithms to numerically solve some of these differential equations. So this is different than using looking at photos on the internet and then having AI generate a new photo. We don't have these solutions. So there isn't a database that you can train an AI model on. But you can still use the framework of these neural networks to try and solve really complicated equations. And indeed, I worked on that, and then lots of other people in the field have, and we found that using these techniques, we can speed up a lot of computations in a really substantive way. And this actually made it possible just recently for groups to compute quark masses in string theory for the first time. So to be clear, these are not the quark mass values that we actually observe in nature. That would be awesome, but we don't see that yet. But we can say, if you just hand me some extra dimensions, whatever they may be, and then say, what would the quarks look like in that universe? Now we can actually come up with those numbers using machine learning algorithms.
Chuck will go back on his ayahuasca trip and get the person from that dimension to verify the quark
mass.
Yeah.
Yeah, exactly.
And Chuck will be the oracle of physics.
And I'm up for it. I'm telling you right now. I'm ready to handle it. I'm ready to go do more ayahuasca. So I'm ready.
So let me ask another thing. You talk about what discoveries can come out of this. Is it possible, because this excites us all, and we don't say it every day, but we feel it. Could any of this bring forth new physics? Because up till now, everything you've said has been within the framework of the quantum field theory, general relativity. And imagine before Einstein was born, you would not even know that relativity was a thing you could use to solve your problems. So is there some new physics waiting to emerge either out of your work or some yet to be born genius that you'll look at and say, oh my gosh? I'm going to give a fast astro case here.
Okay.
At turn of the century, the orbit of Mercury around the sun wasn't quite following Newton's laws. It was like, well, there's probably another planet there tugging on it. Yeah, we even named the planet. I mean, that's how...
Oh, really?
Yeah, we called it Vulcan.
Oh, nice.
Yeah, go 1910. Just look up planet Vulcan. Like, there it is.
Pretty wild.
Okay? And we were happy. Well, how come no one saw it? Oh, because it's too close to the sun.
Right.
It's in the glare. So we had it was all there.
It was all worked out.
All worked out. And then Einstein comes up with general relativity. He wasn't trying to explain it, but he showed that at very strong gravity, Newton's laws fail. You plug into his equations, and there's no disagreement with the thing. So Vulcan died overnight. But the new physics transformed the physics we were already working with and gave us better answers to move on with.
So what I learned from that is Einstein killed Vulcan, Tyson killed Pluto.
Oh, stop! That's not the lesson I was trying to...
It's a good lesson.
No, it's not. No.
So new physics could take a lot of different forms. So one example might be perhaps there are more than the four fundamental forces that we've already observed in nature. So could there be a so-called fifth force, another version of something like electromagnetism or the strong weak nuclear force? That would be an example of new physics. Other things that we know we don't understand very well include things like dark energy and dark matter. Questions like, general relativity tells us that there are these disastrous infinities, in the center of black holes, there's singularities. So what actually repairs those singularities in a quantum, gravitational theory? What tells us how physics really behaves inside there? That's definitely new physics. And that would be the hope of the kind of thing you'd like to see.
Oh, wow.
So you think there's new physics out there?
Not, again, the claims on, what can string theory deliver, I'm still somewhat agnostic on that. But I think it's really interesting to try and push the theory to find out. Say, can you show that this just can't be used to model our universe, which is a real possibility, and it's going to break somewhere you can't get there? Or can you push it to try and make some of this structure visible?
So I'd love 100 years from now, look back on this conversation and say, look at those idiots back in 2025.
Right. Yeah, this will be a kindergarten video 100 years from now.
I hope so.
So I got something else here about a duality in string theory. What's going on there?
Yeah, this is something that I and my collaborators are working on at the moment.
That's a cool word, by the way, duality.
I love duality.
Duality.
So the idea behind duality is that you could have two different theories or two different geometries as they arise for these compact extra dimensions in string theory that secretly are different sides of the same coin. So an analogy that I give sometimes in talks is if you ever looked at some of these optical illusions photos on the internet where, you have a picture that's either a vase if you look at it one way or two faces if you look at it the other way, you can say, is it a vase or is it faces? And the answer is it's both, right? It's both packaged. The question in string theory is you have all these different, 500 million configurations for extra dimensions. Do they all lead to different physics? And the answer that we think is no. There are known equivalences of different so-called topological spaces. These are things that have, a different geometric properties like their number of holes and their structure. Those different topological spaces can actually lead to the same physics that we would see. So that if there's redundancy in that is really powerful because it means you don't have to search through 500 million possibilities. You can, maybe sort of fold those possibilities in half and only look at some portion of them. Some of these dualities have been around for 20 years in string theory, and my collaborators and I think we have new examples which require less supersymmetry, so a less spherical cow than people have assumed in the past.
Okay.
Yeah, we're growing some legs in the cow, for example. And we think that this may improve our ability to calculate lots of things and also teach us some new properties mathematically about how these spaces behave.
Wait, catch us up on supersymmetry.
So supersymmetry is something that comes along for the ride for some formulations of string theory, which says that all the quarks and leptons that we see in nature may have additional partners. So, for example, instead of a quark, you have a squark, another partner that would be much heavier than the existing particles that we've seen.
So when you're describing supersymmetry, it's a symmetry beyond the symmetries that are already known and loved in the standard model.
That's right. So all these sort of 3 generations of quarks and leptons that we've seen already, there would be another whole set of those particles that would share many of their properties but be heavier in mass, and sort of the opposites, and that each theory, each particle that was, say, a boson would have a fermionic partner, and so on.
All right, so what you're saying is you're not content with just these 3 regimes we have in the standard model. Just hand us somewhere in the universe other regimes above that and see what properties they might have. That could explain stuff that we don't now understand.
That's an idea. And people initially thought this idea might explain some really important questions in particle physics, for example, to do with the mass of the Higgs boson. That would be what's called low-scale supersymmetry, and particle experiments like the LHC searched very hard for this and didn't see it. So some people consider supersymmetry not a very useful idea because they thought, it might appear in these regimes and it would not be useful. People are re-investigating this question in string theory. Some of the solutions of string theory are supersymmetric, some are not. What we generally would agree on is that if you did have supersymmetry, it would have to be at a very high scale. So it would be these particles would be much heavier than you could see at an experiment like the LHC, and that the symmetry would be spontaneously broken in universes like ours, so that by the time you got down to, where we live now, you would only see the standard model particles at the energy
and not the other
that
ones that would have helped birth it. So
I'm going to say that's rather convenient, though. I'm just going to say.
So the question is, why do you need that symmetry, right? If you're kind of getting rid of it back when, you really want to be talking about the physics, yeah.
Conveniently discarding it.
Yeah.
That's a great question. In some string theories, it still plays a role in terms of regulating the quantum mechanical behavior of the theory and making it well behaved. So in that sense, you're still using it theoretically for something, even though you don't need it to describe the particle physics that we are observing in nature. But I think all string theorists would ask, it's a really interesting question to say, how much of the supersymmetry can you get rid of and then still preserve the features that are of interest to us? So the types of dualities I was describing, these are perhaps new because they involve less reliance on supersymmetry than we had in the past. And so we're still observing this sort of redundancy, or these different descriptions of the same physics packaged different ways. But we don't need as much supersymmetry.
If memory serves, the graviton is not in the standard model. Is that correct?
That's right.
So that means no one is thinking about a supersymmetric particle to the graviton, because that would be kind of interesting.
Yeah, you certainly could. For any particle, any gauge boson, you could have what's called a gaugino, so a supersymmetric particle.
Gaugino. They're just pulling it out of the ass.
Yes, it sounds like you're naming pharmaceutical products.
This is before my era in physics, but I do feel that some of these names are very much a product of the 1970s.
I was in high school, that's how old I am, in the 1970s, and I'm just, there was the Particle of the Month Club. What new particle was being discovered in the new accelerators in California and elsewhere. And we were just building this fabric of the universe out of that.
That's kind of cool, actually.
It was fun to be witness to it. It was fun.
That's fun.
Yeah, not participant, but
right.
Witness. Could you spend a moment just celebrating the idea of symmetry in physics?
Yeah, this is a really, really great question. So symmetry in physics, this is something that is extremely deep and has been very, very predictive and powerful over the last 100 years of physics. So this is a question that in my classes to undergraduates, I try and convey that a lot of physics is based on looking at a phenomena that you see, like an apple falling from a tree, and saying, how do I model the path that's going to fall, right? Like, how do I write an equation that describes that? But once you start talking about symmetries, and these are basically rules for how you might change a space or an equation in ways that can leave it alone, once you start talking about symmetries, you actually have the power to ask, could the theory that I'm describing be any different? It allows you to ask questions about not just what you observe, but whether any theory that you write down could have arisen differently in nature. So there's some kind of highfalutin quote by Einstein that, saying he wanted to probe God's thoughts, in terms of his theories, which sounds extremely grandiose. But the tangible, non-theological underpinning of that is that you can ask for a theory. If I write down this theory, like Einstein's theory of relativity, could it have been different? What is the freedom to change that theory at all? Could there have been any other theory of gravity that could have worked?
So what does it have to do with our understanding of what the word symmetry means?
Great. So the idea behind symmetries is that if I tell you about the rules for what I can do for a theory and leave it alone, that is equivalent to specifying the theory. So, for example, if you want to ask, how are the laws of physics impacted by the fact that if I do an experiment here, and then I move that experiment 5 feet to the left and do the same experiment, I should get the same answer, right? What is the implication of that for the laws of physics? It turns out that phenomena, that the laws of physics shouldn't care whether your laboratory is here versus 5 feet to the left, that's very much linked to something like the conservation of momentum in classical physics. Or the fact that you should do an experiment today and get the same answer tomorrow is related to the idea that energy is conserved in classical physics. So all of the sort of, can I shift something, in some concrete way? There I talked about, moving an experiment or doing the same experiment at different points in time. But in more general, you can say, if I could characterize all the different ways that I can, pick something up, turn it over, look at it, shift its description, and if it stays the same, that actually tells me what equations are compatible with that in a really predictive way.
I've got another symmetry here, mirror symmetry. So what do you have for us there?
So mirror symmetry was originally discovered in the context of these string compactifications. So considering solutions of string theory that could lead to physics like we see in our universe, the compact extra dimensions that people were trying to write down, they discovered that all the solutions they could find seemed to come in pairs. And these pairs involved interchanging topological numbers. So a topological number is all the ways that you can change a geometry, is characterized by all the ways you can change a geometry without intrinsically changing what it is. So the classic example is that you can change a donut into a coffee cup. So you picture, taking yourself a donut, and if you imagine the material was all rubbery and you could stretch it and squish it any way you want, but not cut it, how can you deform that shape or change it?
Or put another hole in it. And this is a coffee cup with a little finger hole.
With a handle.
Yeah. It wouldn't work if it didn't have a handle. Right.
So if it was just like a drinking glass, it doesn't work.
Yeah, not the coffee cup from Starbucks, because that doesn't have a handle.
Right, okay.
The idea there is that a geometry with a single hole, you can't change the number of holes, whether that's the center of the donut or if you could smush it around and turn it into the handle of a coffee cup. That's what's called a topological invariant. So the number of holes is one of these examples of topological numbers. So a donut has one hole. You could imagine, a donut that was built to have 2 holes, and so on. This kind of thing describes or characterizes geometry. So in mirror symmetry, all these geometries come with topological numbers, but any combinations you could have, it turns out you could have in more than one configuration. And this, again, sort of divides the space of possible geometries in half in this case. It tells you that all of them are interchangeable in concrete ways.
Wow. Man, that is insane. First of all, why?
It's a really great question.
That's so crazy. I love it though.
Well, but I got more here. Where we're just cracking this egg. What do I have? Calabi-Yau manifolds.
So these are examples of configurations for the shapes of extra dimensions in string theory that satisfy Einstein's equations. So these are the 500 million possibilities that I was talking about.
A manifold. Okay, so now I need to get the word manifold.
Yeah, y'all got that from Star Trek. Get out of here.
Named after 2 very clever mathematicians. Yeah, these manifolds were conjectured to exist by a mathematician named Eugene Calabi and proved by Yao, who won a Fields Medal for his proof that these things solved Einstein's equations.
Do you know about the Fields Medal?
No, I don't.
So it's kind of like the Nobel Prize in mathematics. It's given to major, substantive discoveries in mathematics. But the catch is you got to be under 40 to get it. So you have to be young and clever.
Oh, man, of course, the mathematicians would use chronology as a determining factor. Discriminating.
It's ageist. I think
Yes,
it is.
yeah, exactly.
Homological field mirror symmetry.
So this is an example of something where there was a dialogue between string theory and mathematics that was really fruitful. So these observations about Calabi manifolds and their topology were first observed in string theory, and mathematicians went away and tried to sort of explain why that was happening and found a correspondence between a lot of deeper mathematical structures that actually led to another Fields Medal for a gentleman named Kontsevich.
That's Maxim Kontsevich. That sounds Russian.
Yeah,
right?
yes. Exactly.
Yeah.
Uh-huh.
So this type of structure, this dialogue between maths and physics, I personally think is really fruitful. We've learned a lot from mathematicians from building these kinds of things. And then the fun question that I'm asking recently is, could there be new variants of this that could lead to new physics, new predictions for particle physics, but also new mathematical structures? So some of the dualities we're looking at right now involve not just changing two manifolds or two configurations of geometry, but actually mixing things like electromagnetic fields in those backgrounds with geometry. So there's all sorts of weird and wonderful mixing of possible degrees of freedom in the theory that could still magically leave the physics alone.
There's surely plenty of physicists out there who are perfectly trained in all their physics, but don't have your math background. So in a way, they're kind of researching with blinders on, given how much more you see in the mathematical regimes. Is that a fair characterization here?
The pushback, somebody might say, you're sort of torturing yourself by trying to solve really hard problems in math and physics at the same time. So there are lots of questions where you don't need this degree of math. But unfortunately, the path to the physical questions we want to answer leads through this crazy, hairy geometry in high dimensions to be able to answer the physics we want in string theory. So we kind of don't have a choice.
This evokes Einstein, where I don't think he was totally up on non-Euclidean geometry.
Differential geometry, all that.
Different. He wasn't totally up on that and needed some help, right? Even though he had the physics.
Oh, man, I would love to meet Einstein's tutor. What do you do? I tutor Einstein in geometry. That's all. Yeah.
This marriage of frontier physics and emergent math, it's been going since the very beginning. And I might offer a cosmic perspective on that as we close it out.
Alrighty.
One of the features of research scientists in academia is to get really smart people working on problems where there's no obligation or expectation that there's a sellable product at the end of that exercise. What it means is that the mind can roam freely on the boundaries of what is known and unknown in the universe. And in physics, that has always occurred. It's always occurred in tandem with advances in mathematics. You go back to ancient Greece. They're trying to measure the shape of the earth. Is it round? Is it not? The word geometry gets introduced. And if you look at what that means, it means earth measurement, geometry. And so you look at this juxtaposition of our advances in science and our advances in mathematics, and these are two fields that so often people in school say, I'm not good at math and I'm not good at physics. Meanwhile, is the foundation of our understanding of our place and existence in this universe. So I look forward to further advances on the frontier of physics and how they marry with further advances in mathematics, no matter how obscure it might look to the passerby. One day, in the end, you'll be living with it as we currently are, with all the trappings of modern engineering, technology, and society at large. And that's a cosmic perspective. So Lara, this has been a delightful conversation. We've learned a lot, or you've told us a lot. Maybe I learned maybe 2/3 of it. What's your fraction on that?
I am just as dumb as I ever have been. No. But I feel smart.
There you go. That's all that matters. And so, again, you're at Virginia Tech and you teach a course on general relativity, Einstein's relativity. Love it. So you're a pure theorist, right? So they don't invite you into the particle.
Suggests what the company should do. She just makes it all
Be a cautionary warning across his kitchen table in London.
It'll give you some reason to believe that there's a problem there. And if you look at Sam's statements some years ago, he sort of happily said in one interview, this stuff will probably kill us all. That's not exactly what he said, but that's what it amounted to. Now he's saying you don't need to worry too much about it. And I suspect that's not driven by seeking after the truth. That's driven by seeking after money.
Is it money or is it power?
Yeah, I shouldn't have said money. Yes, some combination of those, yes.
Okay, I guess money's a proxy for power, but I've got a friend who's a billionaire and he is in those circles. And when I went to his house and had lunch with him one day, he knows lots of people in AI, building the biggest AI companies in the world. And he gave me a cautionary warning across his kitchen table in London, where he gave me an insight into the private conversations these people have, not the media interviews they do where they talk about safety and all these things, but actually what some of these individuals think is going to happen.
And what do they think is going to happen?
It's not what they say publicly. You know, one person who I shouldn't name, who's leading one of the biggest AI companies in the world, he told me that he knows this person very well, and he privately thinks that we're heading towards this kind of dystopian world where we have just huge amounts of free time, we don't work anymore, and this person doesn't really give a fuck about the harm that it's going to have on the world. And this person, who I'm referring to, is building one of the biggest AI companies in the world. And I then watch this person's interviews online.
Trying to figure out which of three people it is.
Yeah, well, it's one of those three people.
Okay.
And I watch this person's interviews online, and I reflect on a conversation that my billionaire friend had with me, who knows him, and I go, fucking hell, this guy's lying publicly. Like, he's not telling the truth to the world. And that's haunted me a little bit. Part of the reason I have so many conversations around AI on this podcast, because I'm like, I don't know if I think some of them are a little bit sadistic about power. I think they like the idea that they will change the world, that they will be the ones that fundamentally shifts the world.
I think Musk is clearly like that, right?
He's such a complex character that I don't really know how to place Musk.
He's done some really good things, like pushing electric cars. That was a really good thing to do.
Yeah.
Some of the things he said about self-driving were a bit exaggerated, but that was a really useful thing. Giving the Ukrainians communication during the war with Russia. That was a really good thing. There's a bunch of things like that. But he's also done some very bad things.
So coming back to this point of the possibility of destruction and the motives of these big companies, are you at all hopeful that anything can be done to slow down the pace and acceleration of AI?
Okay, there's two issues. One is, can you slow it down?
Yeah.
And the other is, can you make it so that it will be safe in the end? You won't wipe us all out. I don't believe you're going to slow it down.
Yes.
And the reason I don't believe we're going to slow it down is because there's competition between countries and competition between companies within a country, and all of that is making it go faster and faster. And if the US slowed it down, China would slow it down.
Does Ilya think it's possible to make AI safe?
I think he does. He won't tell me what his secret source is. I'm not sure how many people know what his secret source is. I think a lot of the investors don't know what his secret source is. And they've given him billions of dollars anyway, because they have so much faith in him, which isn't foolish. I mean, he was very important in AlexNet, which got object recognition working well. He was the main force behind the things like GPT-2, which then led to ChatGPT. So I think having a lot of faith in him is a very reasonable decision.
There's something quite haunting about the guy that made and was the main force behind GPT-2, which led rise to this whole revolution, left the company because of safety reasons. He knows something that I don't know about what might happen next.
Well, the company had... No, I don't know the precise details, but I'm fairly sure the company had indicated that it would use a significant fraction of its resources of the compute time for doing safety research, and then it reduced that fraction. I think that's one of the things that happened.
Yeah, that was reported publicly.
Yes.
Yeah. We'd gotten to the autonomous weapons part of the risk framework.
Right. So the next one is joblessness.
Yeah.
In the past, new technologies have come in which didn't lead to joblessness. New jobs were created. So the classic example people use is automatic teller machines. When automatic teller machines came in, a lot of bank tellers didn't lose their jobs. They just got to do more interesting things. But here, I think this is more like when they got machines in the Industrial Revolution, and you can't have a job digging ditches now because a machine can dig ditches much better than you can. And I think for mundane intellectual labour, AI is just going to replace everybody. Now, it may well be in the form of you have fewer people using AI assistants. So it's a combination of a person and an AI assistant are now doing the work that 10 people could do previously.
People say that it will create new jobs, though, so we'll be fine.
Yes, and that's been the case for other technologies, but this is a very different kind of technology. If it can do all mundane human intellectual labour, then what new jobs is it going to create? You'd have to be very skilled to have a job that it couldn't just do. So I don't think they're right. I think you can try and generalise from other technologies that come in, like computers or automatic teller machines, but I think this is different.
People use this phrase, they say, AI won't take your job, a human using AI will take your job.
Yes, I think that's true. But for many jobs, that'll mean you need far fewer people. My niece answers letters of complaint to a health service. It used to take her 25 minutes. She'd read the complaint and she'd think how to reply and she'd write a letter. And now she just scans it into a chatbot and it writes the letter. She just checks the letter. Occasionally she tells it to revise it in some ways. The whole process takes her 5 minutes. That means she can answer 5 times as many letters. And that means they need 5 times fewer of her. So she can do the job that 5 of them used to do. Now, that will mean they need less people. In other jobs, like in healthcare, they're much more elastic. So if you could make doctors 5 times as efficient, we could all have 5 times as much healthcare for the same price. And that would be great. There's almost no limit to how much healthcare people can absorb. They always want more healthcare. There's no cost to it. There are jobs where you can make a person with an AI assistant much more efficient, and you won't lead to less people because you'll just have much more of that being done. But most jobs, I think, are not like that.
Am I right in thinking this sort of industrial revolution played a role in replacing muscles?
Yes, exactly.
And this revolution in AI replaces intelligence, the brain?
Yeah. So mundane intellectual labour is like having strong muscles, and it's not worth much anymore.
So muscles have been replaced, now intelligence is being replaced.
Yeah.
So what remains?
Maybe for a while some kinds of creativity, but the whole idea of superintelligence is nothing remains. These things will get to be better than us at everything.
So what do we end up doing in such a world?
Well, if they work for us, we end up getting lots of goods and services for not much effort.
Okay, but that sounds tempting and nice, but I don't know, there's a cautionary tale in creating more and more ease for humans in it going badly.
Yes, and we need to figure out if we can make it go well. So the nice scenario is, imagine a company with a CEO who is very dumb, probably the son of the former CEO, and he has an executive assistant who's very smart, and he says, I think we should do this. And the executive assistant makes it all work. The CEO feels great. He doesn't understand that he's not really in control. And in some sense, he is in control. He suggests what the company should do. She just makes it all work. Everything's great. That's the good scenario.
And the bad scenario?
The bad scenario is she thinks, why do we need him?
Yeah. I mean, in a world where we have superintelligence, which you don't believe is that far away.
Yeah, I think it might not be that far away. It's very hard to predict, but I think we might get it in like 20 years or even less.
I made the biggest investment I've ever made in a company because of my girlfriend. I came home one night and my lovely girlfriend was up at 1 a.m. in the morning pulling her hair out as she tried to piece together her own online store for her business. And in that moment, I remembered an email I'd had from a guy called John, the founder of Standstore, our new sponsor and a company I've invested in things. This channel about since your or Gemini, because I'm excited for you. I am. So what's the difference between what we have now and superintelligence? Because it seems to be really intelligent to me when I use like ChatGPT 3.0 or Gemini or...
Okay, so it's already, AI is already better than us at a lot of things. In particular areas, like chess, for example.
Yeah.
AI is so much better than us that people will never beat those things again. Maybe the occasional thing, but basically they'll never be possible again. Obviously the same in Go. In terms of the amount of knowledge they have, something like GPT-4 knows thousands of times more than you do. There's a few areas in which your knowledge is better than us, and almost all areas it just knows more than you do.
What areas am I better than it?
Probably in interviewing CEOs. You're probably better at that. You've got a lot of experience at it. You're a good interviewer. You know a lot about it. If you got GPT-4 to interview a CEO, probably do a worse job.
Okay. I'm trying to think if I agree with that statement. GPT-4, I think, for sure.
Yeah.
But I guess you could train one.
But it may not be long before.
Yeah, I guess you could train one on this, how I ask questions and what I do. And
sure. And if you took a general purpose sort of foundation model and then you trained it up on not just you, but every interviewer you could find doing interviews like this, but especially you would probably get to be quite good at doing your job, but probably not as good as you for a while.
Okay. So there's a few areas left, and then superintelligence becomes when it's better than us at all things.
When it's much smarter than you, and almost all things it's better than you, yeah.
And you say that this might be a decade away or so.
Yeah, it might be. It might be even closer. Some people think it's even closer. It might well be much further. It might be 50 years away. That's still a possibility. It might be that somehow training on human data limits you to not be much smarter than humans. My guess is between 10 and 20 years we'll have superintelligence.
On this point of joblessness, it's something that I've been thinking a lot about in particular because I started messing around with AI agents. And we released an episode on the podcast actually this morning where we had a debate about AI agents with a CEO of a big AI agent company and a few other people. And it was the first moment where it was another moment where I had a eureka moment about what the future might look like. When I was able, in the interview, to tell this agent to order all of us drinks, and then 5 minutes later in the interview, you see the guy show up with the drinks, and I didn't touch anything. I just told it to order us drinks to the studio.
And it didn't know about who you normally got your drinks from. It figured that out from the web.
Yeah, figured it out because it went on Uber Eats. It has my data, I guess. And we put it on the screen in real time so everyone at home can see the agent going through the internet, picking the drinks, adding a tip for the driver, putting my address in, putting my credit card details in, and then the next thing you see is the drinks show up. So that was one moment. And then the other moment was when I used a tool called Replit, and I built software by just telling the agent what I wanted.
Yes, it's amazing, right?
It's amazing and terrifying at the same time.
Yes.
Because...
And if it can build software like that, right?
Yeah.
Remember that the AI, when it's training, is using code. And if it can modify its own code, then it gets quite scary, right?
Because it can modify itself.
It can change itself in a way we can't change ourselves. We can't change our innate endowment, right? There's nothing about itself that it couldn't change.
On this point of joblessness, you have kids.
I do.
And they have kids?
No.
They don't have kids, so no grandkids yet. What would you be saying to people about their career prospects in a world of superintelligence? What should we be thinking about?
In the meantime, I'd say it's going to be a long time before it's as good at physical manipulation as us.
Okay.
And so a good bet would be to be a plumber.
Until the humanoid robots show up. In such a world where there is mass joblessness, which is not something that you just predict, but this is something that Sam Altman at OpenAI, I've heard him predict, and many of the CEOs, Elon Musk, I watched an interview which I'll play on screen of him being asked this question, and it's very rare that you see Elon Musk silent for 12 seconds or whatever it was.
Right.
And then he basically says something about he actually is living in suspended disbelief, i.e. he's basically just not thinking about it.
When you think about advising your children on a career with so much that is changing, what do you tell them is going to be of value?
Well, that is a tough question to answer. I would just say, to sort of follow their heart in terms of what they find interesting to do or fulfilling to do. I mean, if I think about it too hard, it frankly can be dispiriting and demotivating. Because, I mean, I go through, I've put a lot of blood, sweat, and tears into building the companies, and then I'm like, should I be doing this? Because if I'm sacrificing time with friends and family, that I would prefer to do. But then ultimately the AI can do all these things. Does that make sense? I don't know. To some extent, I have to have deliberate suspension of disbelief in order to remain motivated. So I guess I would say just, work at things that you find interesting, fulfilling, and that contribute some good to the rest of society.
Yeah, a lot of these threats, it's very hard to, intellectually you can see the threat, but it's very hard to come to terms with it emotionally.
Yeah.
I haven't come to terms with it emotionally.
What do you mean?
I haven't come to terms with what the development of superintelligence could do to my children's future. I'm okay, I'm 77. I'm going to be adults. But for my children and my younger friends, my nephews and nieces, and their children, I just don't like to think about what could happen.
Why?
Because it could be awful.
In what way?
Well, if AI was right to take over, I mean, it would need people for a while to run the power stations until it designed better analog machines to run the power stations. There's so many ways it could get rid of people, all of which would, of course, be very nasty.
Is that part of the reason you do what you do now?
Yeah. I mean, I think we should be making a huge effort right now to try and figure out if we can develop it safely.
Are you concerned about the midterm impact potentially on your nephews and your kids in terms of their jobs as well?
Yeah, I'm concerned about all that.
Are there any particular industries that you think are most at risk? People talk about the creative industries a lot and sort of knowledge work. They talk about lawyers and accountants and stuff like that.
Yeah, so that's why I mentioned plumbers. I think plumbers are less at risk. Someone like a legal assistant, a paralegal, they're not going to be needed very long.
And is there a wealth inequality issue here that will rise?
I think in a society which shared out things fairly, if you get a big increase in productivity, everybody should be better off. But if you can replace lots of people by AIs, then the people who get replaced will be worse off. And the company that supplies the AIs will be much better off. And the company that uses the AIs. So it's going to increase the gap between rich and poor. And we know that if you look at that gap between rich and poor, that basically tells you how nice the society is. If you have a big gap, you get very nasty societies in which people live in walled communities and put other people in mass jails. It's not good to increase the gap between rich and poor.
The International Monetary Fund has expressed profound concerns that generative AI could cause massive labour disruptions and rising inequality, and has called for policies that prevent this from happening. I read that in the Business Insider. So
have they given any idea of what the policies should look like?
No.
Yeah, that's the problem. I mean, if AI can make everything much more efficient and get rid of people for most jobs, or have a person assisted by AI doing many people's work, it's not obvious what to do about it.
Universal basic income? Give everybody money?
Yeah, I think that's a good start, and it stops people starving. But for a lot of people, their dignity is tied up with their job. I mean, who you think you are is tied up with you doing this job, right?
Yeah.
And if we said, we'll give you the same money just to sit around, that would impact your dignity.
You said something earlier about it surpassing or being superior to human intelligence. A lot of people, I think, like to believe that AI is on a computer and it's something you can just turn off if you don't like it.
Well, let me tell you why I think it's superior.
Okay.
It's digital. And because it's digital, you can simulate a neural network on one piece of hardware,
Yeah.
and you can simulate exactly the same neural network on a different piece of hardware. So you can have clones of the same intelligence. Now, you could get this one to go off and look at one bit of the internet, and this other one to look at a different bit of the internet. And while they're looking at these different bits of the internet, they can be syncing with each other, so they keep their weights the same. The connection strengths the same. Weights are connection strengths. So this one might look at something on the internet and say, oh, I'd like to increase this strength of this connection a bit. And it can convey that information to this one, so it can increase the strength of that connection a bit based on this one's experience.
And when you say the strength of the connection, you're talking about learning.
That's learning, yes.
Yeah.
Learning consists of saying, instead of this one giving 2.4 votes for whether that one should turn on, we'll have this one give 2.5 votes for whether this one should turn on. Now, that would be a little bit of learning. So these two different copies of the same neural net are getting different experiences. They're looking at different data, but they're sharing what they've learned by averaging their weights together. And they can do that averaging at you can average 1 trillion weights. When you and I transfer information, we're limited to the amount of information in a sentence. And the amount of information in a sentence is maybe 100 bits. It's very little information. We're lucky if we're transferring like 10 bits a second. These things are transferring trillions of bits a second. So they're billions of times better than us at sharing information. And that's because they're digital, and you can have 2 bits of hardware using the connection strengths in exactly the same way. We're analog and you can't do that. Your brain's different from my brain. And if I could see the connection strengths between all your neurons, it wouldn't do me any good, because my neurons work slightly differently and they're connected up slightly differently. So when you die, all your knowledge dies with you. When these things die, suppose you take these 2 digital intelligences that are clones of each other, and you destroy the hardware they run on. As long as you've stored the connection strength somewhere, you can just build new hardware that executes the same instructions, so it'll know how to use those connection strengths, and you've recreated that intelligence. So they're immortal. We've actually solved the problem of immortality, but it's only for digital things.
So it will essentially know everything that humans know, but more, because it will learn new things.
It will learn new things. It will also see all sorts of analogies that people probably never saw. So, for example, at the point when GPT-4 couldn't look on the web, I asked it, why is a compost heap like an atom bomb? Off you go.
I have no idea.
Exactly. Excellent. That's exactly what most people would say. It said, well, the time scales are very different, and the energy scales are very different. But then it went on to talk about how a compost heap, as it gets hotter, generates heat faster. And an atom bomb, as it produces more neutrons, generates neutrons faster. And so they're both chain reactions, but at very different time and energy scales. And I believe GPT-4 had seen that during its training. It had understood the analogy between a compost heap and an atom bomb. And the reason I believe that is, if you've only got 1 trillion connections, remember you have 100 trillion, and you need to have thousands of times more knowledge than a person, you need to compress information into those connections. And to compress information, you need to see analogies between different things. In other words, it needs to see all the things that are chain reactions and understand the basic idea of a chain reaction and code that, and then code the ways in which they're different. And that's just a more efficient way of coding things than coding each of them separately. So it's seen many, many analogies, probably many analogies that people have never seen. That's why I also think that people say these things will never be creative. They're going to be much more creative than us, because they're going to see all sorts of analogies we never saw. And a lot of creativity is about seeing strange analogies.
People are somewhat romantic about the specialness of what it is to be human. And you hear lots of people saying, it's very, very different, it's a computer. We are, we're conscious, we are creatives, we have these sort of innate, unique abilities that the computers will never have. What do you say to those people?
I'd argue a bit with the innate. So the first thing I say is we have a long history of believing people were special, and we should have learned by now. We thought we were at the center of the universe. We thought we were made in the image of God. White people thought they were very special. We just tend to want to think we're special. My belief is that more or less everyone has a completely wrong model of what the mind is. Let's suppose I drink a lot, or I drop some acid, and not recommended. And I say to you, I have the subjective experience of little pink elephants floating in front of me. Most people interpret that as there's some kind of inner theatre called the mind, and only I can see what's in my mind. And in this inner theatre, there's little pink elephants floating around. So in other words, what's happened is my perceptual system's gone wrong, and I'm trying to indicate to you how it's gone wrong and what it's trying to tell me. And the way I do that is by telling you what would have to be out there in the real world for it to be telling the truth. And so these little pink elephants, they're not in some inner theatre. These little pink elephants are hypothetical things in the real world. And that's my way of telling you how my perceptual system's telling me fibs. So now let's do that with a chatbot. Because I believe that current multimodal chatbots have subjective experiences. And very few people believe that, but I'll try and make you believe it. So suppose I have a multimodal chatbot. It's got a robot arm so it can point, and it's got a camera so it can see things. And I put an object in front of it, and I say, point at the object. It goes like this. No problem. Then I put a prism in front of its lens. And so then I put an object in front of it, and I say, point at the object, and it goes there. Good. And I say, no, that's not where the object is. The object's actually straight in front of you, but I put a prism in front of your lens. And the chatbot says, oh, I see, the prism bent the light rays, so the object's actually there, but I had the subjective experience that it was there. Now, if the chatbot says that, it's using the word subjective experience exactly the way people use it. It's an alternative view of what's going on. They're hypothetical states of the world, which, if they were true, would mean my perceptual system wasn't lying. And that's the best way I can tell you what my perceptual system's doing when it's lying to it. Now, we need to go further to deal with sentience and consciousness and feelings and emotions. But I think in the end, they're all going to be dealt with in a similar way. There's no reason machines can't have them. But people say machines can't have feelings. And people are curiously confident about that. I've no idea why. Suppose I make a battle robot. And it's a little battle robot. And it sees a big battle robot that's much more powerful than it. It would be really useful if it got scared. Now, when I get scared, various physiological things happen that we don't need to go into. And those won't happen with the robot. But all the cognitive things, like I better get the hell out of here, and I better sort of change my way of thinking so I focus and focus and focus and don't get distracted, all of that will happen with robots too. People will build in things so that they, when the circumstances are such they should get the hell out of there, they get scared and run away. They'll have emotions then. They won't have the physiological aspects, but they will have all the cognitive aspects. And I think it would be odd to say they're just simulating emotions. No, they're really having those emotions. The little robot got scared and ran away.
It's not running away because of adrenaline, it's running away because of a sequence of sort of neurological, in its neural net, processes happened,
which have the equivalent effect to adrenaline.
So do you
and
think...
it's not just adrenaline, right? There's a lot of cognitive stuff goes on when you get scared.
Yeah. So do you think that there is conscious AI? And when I say conscious, I mean that represents the same properties of consciousness that a human has.
There's two issues here. There's a sort of empirical one and a philosophical one. I don't think there's anything in principle that stops machines from being conscious. I'll give you a little demonstration of that before we carry on. Suppose I take your brain, and I take one brain cell in your brain, and I replace it by, this is a bit Black Mirror-like, I replace it by a little piece of nanotechnology that's just the same size, that behaves in exactly the same way when it gets pings from other neurons. It sends out pings just as the brain cell would have. So the other neurons don't know anything's changed. Okay, I've just replaced one of your brain cells with this little piece of nanotechnology. Would you still be conscious?
Yeah.
Now you can see where this argument's going.
Yeah, so if you replaced all of them.
As I replace them all, at what point do you stop being conscious?
Well, people think of consciousness as this, like, ethereal thing that exists maybe beyond the brain cells.
Yeah, well, people have a lot of crazy ideas. people don't know what consciousness is, and they often don't know what they mean by it. And then they fall back on saying, well, I know it because I've got it and I can see that I've got it. And they fall back on this theatre model of the mind, which I think is nonsense.
What do you think of consciousness as, if you had to try and define it? Is it, because I think of it as just like the awareness of myself, I don't know.
I think it's a term we'll stop using. Suppose you want to understand how a car works. Well, you know, some cars have a lot of oomph, and other cars have a lot less oomph. Like an Aston Martin's got lots of oomph, and a little Toyota Corolla doesn't have much oomph. But oomph isn't a very good concept for understanding cars. If you want to understand cars, you need to understand about electric engines or petrol engines and how they work. And it gives rise to oomph, but oomph isn't a very useful explanatory concept. It's the kind of essence of a car. It's the essence of an Aston Martin, but it doesn't explain much. I think consciousness is like that, and I think we'll stop using that term. But I don't think there's any reason why a machine shouldn't have it. If your view of consciousness is that it intrinsically involves self-awareness, then the machine's got to have self-awareness. It's got to have cognition about its own cognition and stuff. But I'm a materialist through and through, and I don't think there's any reason why a machine shouldn't have consciousness.
Do you think they do, then, have the same consciousness that we think of ourselves as being uniquely given as a gift when we're born?
I'm ambivalent about that at present. So I don't think there's this hard line. I think as soon as you have a machine that has some self-awareness, it's got some consciousness. I think it's an emergent property of a complex system. It's not a sort of essence that's throughout the universe. It's, you make this really complicated system that's complicated enough to have a model of itself, and it does perception. And I think then you're beginning to get a conscious machine. So I don't think there's any sharp distinction between what we've got now and conscious machines. I don't think it's going to, one day we're going to wake up and say, hey, if you put this special chemical in, it becomes conscious. It's not going to be like that.
I think we all wonder if these computers are like thinking like we are on their own when we're not there, and if they're experiencing emotions, if they're contending with, I think we probably, you know, we think about things like love and things that feel unique to biological species. Are they sat there thinking? Do they have concerns?
I think they really are thinking. And I think as soon as you make AI agents, they will have concerns. If you want to make an effective AI agent, suppose let's take a call center. In a call center, you have people. They have all sorts of emotions and feelings, which are kind of useful. So suppose I call up the call center, and I'm actually lonely, and I don't actually want to know the answer to why my computer isn't working. I just want somebody to talk to. After a while, the person in the call center will either get bored or get annoyed with me and will terminate it. Well, you replace them by an AI agent. The AI agent needs to have the same kind of responses. If someone's just called up because they just want to talk to the AI agent and we're happy to talk for the whole day to the AI agent, that's not good for business. And you want an AI agent that either gets bored or gets irritated and says, I'm sorry, but I don't have time for this. And once it does that, I think it's got emotions. Now, like I say, emotions have two aspects to them. There's the cognitive aspect and the behavioral aspect, and then there's the physiological aspect. And those go together with us. And if the AI agent gets embarrassed, it won't go red.
Yeah. So there's no physiological...
And its skin won't start sweating.
Yeah.
But it might have all the same behavior. And in that case, I'd say, yeah, it's having emotion. It's got an emotion.
So it's going to have the same sort of cognitive thought, and then it's going to act upon that cognitive
in
thought.
The same way, but without the physiological responses.
And does that matter? That it doesn't go red in the face, and it's just a different... I mean, that's a response to the...
It makes it somewhat different from us.
Yeah.
For some things, the physiological aspects are very important, like love. They're a long way from having love the same way we do. But I don't see why they shouldn't have emotions. So I think what's happened is people have a model of how the mind works and what feelings are and what emotions are, and their model is just wrong.
What brought you to Google? You worked at Google for about a decade, right?
Yeah.
What brought you there?
I have a son who has learning difficulties, And in order to be sure he would never be out on the
You seem
street,
comfortable out there.
I needed
I'm
to
sure you will get your PPL
several
in no
million
time.
dollars, and I wasn't going to get that as an academic. I tried, so I taught a Coursera course in the hope that I'd make lots of money that way, but there was no money in that. So I figured out, well, the only way to get millions of dollars is to sell myself to a big company. And so when I was 65, fortunately for me, I had two brilliant students who produced something
There's a
called
laptop in the
AlexNet,
office
which
that
was
shows all the
neural net that was
certification
very good at
information
recognizing
you will
objects and
need
images.
for your PPL exam.
And
Take a look.
so Ilya and Alex and I set up a little company and auctioned it. And we actually set up an auction
Here you
where
can
we
see
had
all the
a number of
different
big companies
certifications
bidding
you
for
can
us.
pass throughout your career.
And that company was called AlexNet.
No, the network
Your
that
first
recognized
step is
objects
to
was
work
called
towards your
AlexNet.
private
The
pilot
company was
license.
called DNN Research, Deep Neural Network Research.
And it was doing things like this. I'll put this graph up on the screen.
That's AlexNet.
This picture shows 8 images, and
All the training
AlexNet's
lessons you will
ability,
need to
which is
pass
your
the
company's
PPL
ability
exam
to
are
spot
available
what was
here.
in those images.
Make sure you're
Yeah.
comfortable with these.
So it could
before
tell the
taking
difference
exam.
between various kinds of mushroom. And about 12% of ImageNet is dogs. And to be good at ImageNet, you have to tell the difference between very similar kinds of dog. And we've got to be very good at that.
And your company, AlexNet, won several awards, I believe, for its ability to outperform its competitors. And so Google ultimately ended up acquiring your technology.
Google acquired that technology and some other technology.
And you went to work at Google at age, 66?
I went at age 65 to work at Google.
65. And you left at age 76?
75.
75, okay.
I worked there for more or less exactly 10 years.
And what were you doing there?
Okay, they were very nice to me. They said pretty much you can do what you like. I worked on something called distillation that did really work well. And that's now used all the time
In AI.
in AI. And distillation is a way of taking what a big model knows, a big neural net knows, and getting that knowledge into a small neural net. Then at the end, I got very interested in analog computation and whether it would be possible to get these big language models running in analog hardware so they used much less energy. And it was while I was doing that work that I began to really realize how much better digital is for sharing information.
Was there a eureka moment?
There was a eureka month or two, and it was a sort of coupling of ChatGPT coming out, although Google had very similar things a year earlier, and I'd seen those, and that had a big effect on me. The closest I had to a eureka moment was when a Google system called Palm was able to say why a joke was funny. And I'd always thought of that as a kind of landmark. If it can say why a joke's funny, it really does understand. And it could say why a joke was funny. And that coupled with realizing why digital is so much better than analog for sharing information suddenly made me very interested in AI safety and that these things were going to get a lot smarter than us.
Why did you leave Google?
The main reason I left Google was because I was 75 and I wanted to retire. I've done a very bad job of that. The precise timing of when I left Google was so that I could talk freely at a conference at MIT. But I left because I'm old and I was finding it harder to program. I was making many more mistakes when I programmed, which was very annoying.
You wanted to talk freely at a conference at MIT.
Yes, at MIT, organized by MIT Tech Review.
What did you want to talk about freely?
AI safety.
And you couldn't do that while you were at Google?
Well, I could have done it while I was at Google, and Google encouraged me to stay and work on AI safety and said I could do whatever I liked on AI safety. You kind of censor yourself. If you work for a big company, you don't feel right saying things that'll damage the big company. Even if you could get away with it, it just feels wrong to me. I didn't leave because I was cross with anything Google was doing. I think Google actually behaved very responsibly.
For this
When they
lesson,
had these big
we're going to
chatbots,
use
they
a line
didn't
drawn on
release
the
them.
windshield to indicate the crew's
Possibly because
attitude.
they were worried about their reputation. They had a
I've
very
also
good
added another
reputation,
dotted
and they
line
didn't
to
want
help
to
you
damage
bank
it.
properly for left
So
turns.
OpenAI didn't have a reputation, and so they could afford
Gently
to
move the
take
yoke
the
to the
gamble.
left until
I mean,
the
there's also
dotted
a
line
big
matches up
conversation
with the
happening
horizon.
around how it will
Then
cannibalize
maintain
their
that
core
bank.
business in search.
There is now, yes.
Yeah.
Yeah.
And it's the old innovator's dilemma to some degree, I guess,
Exactly.
that they're
Yes, it is.
contending with. Bad skin, I've had it. and I'm sure many of you listening have had it too. Or maybe you have it right now. I know how draining it can be, especially if you're in a job where you're presenting often like I am. So let me tell you about something that's helped both my partner and me and my sister, which is red light therapy. I only got into this a couple of years ago, but I wish I'd known a little bit sooner. I've been using our show sponsors Bon Charge's infrared sauna blanket for a while now, but I just got hold of their red light therapy mask as well. Red light has been proven to have so many benefits for the body. Like any area of your skin that's exposed will see a reduction in scarring, wrinkles, and even blemishes. It also helps with complexion. It boosts collagen, and it does that by targeting the upper layers of your skin. And Bon Charge ships worldwide with easy returns and a year-long warranty on all of their products. So if you'd like to try it yourself, head over to boncharge.com/diary and use code DIARY for 25% off any product site-wide. Just make sure you order through this link, boncharge.com/diary with code DIARY. Make sure you keep what I'm about to say to yourself. I'm inviting 10,000 of you to come even deeper into the Diary of a CEO. Welcome to my inner circle. This is a brand new private community that I'm launching to the world. We have so many incredible things that happen that you are never shown. We have the briefs that are on my iPad when I'm recording the conversation. We have clips we've never released. We have behind the scenes conversations with the guests, and also the episodes that we've never ever released, and so much more. In the circle, you'll have direct access to me. You can tell us what you want this show to be, who you want us to interview, and the types of conversations you would love us to have. But remember, for now, we're only inviting the first 10,000 people that join before it closes. So if you want to join our private closed community, head to the link in the description below or go to doaccircle.com. I will speak to you then. I'm continually shocked by the types of individuals that listen to this conversation because they come up to me sometimes. So I hear from politicians, I hear from some rural people, I hear from entrepreneurs all over the world, whether they are the entrepreneurs building some of the biggest companies in the world or they're, early stage startups. For those people that are listening to this conversation now, that are in positions of power and influence, world leaders, let's say, what's your message to them?
I'd say what you need is highly regulated capitalism. That's what seems to work best.
And what would you say to the average person? Doesn't work in the industry, somewhat concerned about the future, doesn't know if they're helpless or not. What should they be doing in their own lives?
My feeling is there's not much they can do. This isn't going to be decided by, just as climate change isn't going to be decided by people separating out the plastic bags from the compostables. That's not going to have much effect. It's going to be decided by whether the lobbyists for the big energy companies can be kept under control. I don't think there's much people can do to, except for try and pressure their governments to force the big companies to work on AI safety. That they can do.
You've lived a fascinating winding life. I think one of the things most people don't know about you is that your family has a big history of being involved in tremendous things. You have a family tree, which is one of the most impressive that I've ever seen or read about. Your great-grandfather, George Bull, founded the Boolean algebra logic, which is one of the foundational principles of modern computer science. You have your great-great-grandmother, Mary Everest Bull, who was a mathematician and educator who made huge leaps forward in mathematics from what I was able to ascertain. The list goes on and on and on. I mean, your great-great-uncle, George Everest, is what Mount Everest is named after. Is that correct?
I think he's my great-great-great-uncle. His niece married George Bull. So Mary Bull was Mary Everest Bull. She was the niece of Everest.
And your first cousin once removed, Joan Hinton, was involved in a nuclear physicist who worked on the Manhattan Project, which is the World War II development of the first nuclear bomb.
Yeah, she was one of the 2 female physicists at Los Alamos. And then, after they dropped the bomb, she moved to China.
Why?
She was very cross with them dropping the bomb, and her family had a lot of links with China. Her mother was friends with Chairman Mao. Quite weird.
When you look back at your life, Jeffrey, with the hindsight you have now and the retrospective clarity, What might you have done differently if you were advising me?
I guess I have 2 pieces of advice. One is, if you have an intuition that people are doing things wrong and there's a better way to do things, don't give up on that intuition just because people say it's silly. Don't give up on the intuition until you've figured out why it's wrong. Figured out for yourself why that intuition isn't correct. And usually it's wrong if it disagrees with everybody else, and you'll eventually figure out why it's wrong. But just occasionally you'll have an intuition that's actually right and everybody else is wrong. And I lucked out that way. Early on I thought neural nets are definitely the way to go to make AI. And almost everybody said that was crazy. And I stuck with it because I couldn't, it just seemed to me it was obviously right. Now, the idea that you should stick with your intuitions isn't going to work if you have bad intuitions. But if you have bad intuitions, you're never going to do anything anyway, so you might as well stick with them.
And in your own career journey, is there anything you look back on and say, with the hindsight I have now, I should have taken a different approach at that juncture?
I wish I'd spent more time with my wife. And with my children when they were little. I was kind of obsessed with work.
Your wife passed away?
Yeah.
From ovarian cancer?
No, well, that was another wife. I had 2 wives died of cancer.
Oh, really? Sorry.
The first one died of ovarian cancer, and the second one died of pancreatic cancer.
And you wish you'd spent more time with her?
With the second wife, yeah. Who was a wonderful person.
Why do you say that in your 70s? What is it that you've figured out that I might not know yet?
Oh, just because she's gone and I can't spend more time with her now.
Mm-hmm. But you didn't know that at the time.
At the time, you think, I mean, it was likely I would die before her just because she was a woman and I was a man. I just didn't spend enough time when I could.
I think I inquire there because I think there's many of us that are so consumed with what we're doing professionally that we kind of assume immortality with our partners because they've always been there. So we,
yeah.
I mean,
but she was very supportive of me spending a lot of time working.
And why do you say your children as well? What's the
Well, I didn't spend enough time with them when they were little.
And you regret that now?
Yeah.
If you had a closing message for my listeners about AI and AI safety, what would that be, Jeffrey?
There's still a chance that we can figure out how to develop AI that won't want to take over from us. And because there's a chance, we should put enormous resources into trying to figure that out. Because if we don't, it's going to take over.
And are you hopeful?
I just don't know. I'm agnostic.
You must get in bed at night, and when you're thinking to yourself about probabilities of outcomes, there must be a bias in one direction. Because there certainly is for me. I mean, imagine everyone listening now has a internal prediction that they might not say out loud, but of how they think it's going to play out.
I really don't know. I genuinely don't know. I think it's incredibly uncertain. When I'm feeling slightly depressed, I think people are toast. The AI is going to take over. When I'm feeling cheerful, I think we'll figure out a way.
Maybe one of the facets of being a human is because we've always been here, like we were saying about our loved ones and our relationships, we assume casually that we will always be here and we'll always figure everything out. But there's a beginning and an end to everything, as we saw from the dinosaurs.
Yeah, and we have to face the possibility that unless we do something soon, near the end.
We have a closing tradition in this podcast where the last guest leaves a question in the diary. And the question that they've left for you is, with everything that you see ahead of us, what is the biggest threat you see to human happiness?
I think the joblessness is a fairly urgent short-term threat to human happiness. I think if you make lots and lots of people unemployed, even if they get universal basic income, they're not going to be happy.
Because they need purpose
Because they need purposes.
and struggle.
They need to feel they're contributing something, they're useful.
And do you think the outcome that there's going to be huge job displacement is more probable than not?
Yes, I do.
And what's
So that one I think is definitely more probable. If I worked in a call centre, I'd be terrified.
And what's the time frame for that in terms of mass?
I think it's beginning to happen already. I read an article in the Atlantic recently that said it's already getting hard for university graduates to get jobs. And part of that may be that people are already using AI for the jobs they would have got.
I spoke to the CEO of a major company that everyone will know of, lots of people use, and he said to me in DMs that they used to have just over 7,000 employees. He said by last year they were down to, I think, 5,000. He said right now they have 3,600. And he said by the end of summer, because of AI agents, they'll be down to 3,000. So
it's happening already.
Yes. He's halved his workforce because AI agents can now handle 80% of the customer service inquiries and other things. So it's happening already.
Yeah.
So urgent action is needed.
Yep.
I don't know what that urgent action is.
That's a tricky one because that depends very much on the political system. And political systems are all going in the wrong direction at present.
I mean, what do we need to do? Save up money? Like, do we save money? Do we move to another part of the world?
I don't know.
What would you tell your kids to do? They said, Dad, like, there's going to be loads of job displacement.
Because I worked for Google for 10 years, they have enough money.
Okay, fine.
So they're not typical.
What if they didn't have money?
Trained to be a plumber.
Really?
Yeah.
Jeffrey, thank you so much. You're the first Nobel Prize winner that I've ever had a conversation with, I think, in my life. So that's a tremendous honor. And you received that award for a lifetime of exceptional work in pushing the world forward in so many profound ways that will lead to great, and that have led to great advancements and things that matter so much to us. And now you've turned this season in your life to shining a light on some of your own work, but also on the broader risks of AI and how it might impact us adversely. And there's very few people that have worked inside the machine of a Google or a big tech company that have contributed to the field of AI that are now at the very forefront of warning us against the very thing that they worked upon.
There are actually a surprising number of us now.
They're not as public, and they're actually quite hard to get to have these kinds of conversations because many of them are still in that industry. So, someone who tries to contact these people often and invites them to have conversations, they often are a little bit hesitant to speak openly. So they speak privately, but they're less willing to openly because maybe they still have some sort of incentives at play.
I have an advantage over them, which is I'm older, so I'm unemployed, so I can say what I like.
Well, there you go. So thank you for doing what you do. It's a real honor, and please do continue to do it.
Thank you.
Thank you so much.
People think I'm joking when I say that, but I'm not.
The plumbing thing.
Yeah. And plumbers are pretty well paid.
Culture treats fathers is wrong. The myths we carry about fathers are wrong. Men have a very specific role in child development, and I wasn't expecting to find this when I first started, but it's fundamental for a child to thrive and survive and be successful. So what we're finding is...
This has always blown my mind a little bit. 53% of you that listen to this show regularly haven't yet subscribed to this show. So could I ask you for a favor before we start? If you like the show and you like what we do here and you want to support us, the free, simple way that you can do just that is by hitting the subscribe button. And my commitment to you is if you do that, then I'll do everything in my power, me and my team, to make sure that this show is better for you every single week. We'll listen to your feedback, we'll find the guests that you want me to speak to, and we'll continue to do what we do. Thank you so much. Dr. Anna Machin, what is the mission you've so far committed your life to? And I guess adding to that, why?
I've committed the last 2 decades of my life to understanding human love and understanding human close relationships. Because as an anthropologist, I understand that love sits at the centre of what it is to be human. If you strip everything else away and you've got your food, you've got your water, the next thing you need are your relationships, is your love. And we are so lucky as a species to experience love in quite a complex way with many different types of people and beings. And we know that it's like the number one thing in terms of your health, mental, physical, your longevity, your happiness, your well-being. And I think we need to understand it, particularly in a world where we're starting to get a lot of input in terms of technology and AI, and the world is getting quicker. We need to go back to who we are really at our core and what love really is. And I suppose that's what I've given my life over to, is to really explain to people, who are you? Because your love is your identity, essentially.
And you use the word anthropologist there. What is an anthropologist?
Okay, so an anthropologist is somebody who studies the human species. I'm an evolutionary anthropologist, which means I sit at the scientific end of it. You can sit at sort of the cultural end or the scientific end. And I study how evolution has shaped us and also why things evolved. So, for example, why did love evolve? Why did fatherhood evolve? And I use lots and lots of different techniques, scanning and genetics and all these different things to be able to answer that question.
I've got another book sat in front of me here, which is, I guess, somewhat linked to love, which is about fathers.
Yeah.
So how did these two things come together? We've got a book here about love, and then we've got a book about fatherhood, and you're very well known for talking on the subject of fatherhood. What is the link? How did the link come to be? And why? Why are you talking about fatherhood?
We have the wrong idea about fathers. The way our culture deals with fathers, treats fathers, is wrong. The myths we carry about fathers are wrong. The influence they have on their children and ultimately on our society is fundamental. So the link came because I had a child. And like most couples who have a baby, we talked about it. We were like, we're going to start trying to have a baby. Then we became pregnant, which was great. Did the pregnancy test together, went to the antenatal classes, went to the scans, all wonderful. Went in to have the baby, and it didn't turn out how it was supposed to. I was very, very ill. I lost a lot of blood. My daughter was poorly when she was born. And afterwards, I was offered loads of counselling. Would you like a debrief? Would you like? And I was like, well, to be absolutely honest, I'm okay, because I passed out. I literally don't remember anything. But my husband witnessed it all. And he basically saw a car crash in slow motion with two people in it who he loved very deeply. And I completely understand why. It was a very stressful information, but nobody explained to him what was happening. And so they mopped me up, took my baby, took her to neonatal care, and left him in the room on his own. And I was breathing very shallowly, and he was scared. And the cleaner came in and said, and was cleaning away, and he just said to the cleaner, do you think she's dead? Because I was breathing so shallowly. And the cleaner went, no, I don't think so, mate. I think they would have told you if she was dead. But after that, he couldn't talk about the birth. He couldn't imagine the birth. He couldn't deal with the emotions from the birth for a good 2 years afterwards. And he was really worried about having another kid. And this made me really angry, actually, because I was like, hold on, we went into this together, and he's literally been discarded, like he doesn't matter. And to me, he's fundamentally important. And then as our daughter grew, I saw the amazing bond he built with her, how integral he was to her life. And so when I went back to university at Oxford to study and to do my work, I thought, well, I'm an anthropologist. Okay, let's look up what do we know about fathers in our society. And there was literally nothing. There was a lot of work on absent fathers, and their impact is fundamental. We know that. And there was a lot of quite stereotypical work on young fathers, teenage fathers. Nothing on the majority of dads who, whether they co-reside or not, stick around. So I started with some really simple questions. What happens to a man when he becomes a father? Does he alter biologically, psychologically? How does he build his bond with his child? What's the nature of that bond? Does he have a role in child development separate to that to mum? Because when I started 20 years ago, the mantra was dads didn't undergo any changes. Dads did not have a bond like mum to their children. It was not as intense, and it certainly wasn't an attachment relationship, which we all know are really intense, important relationships. And as an evolutionary anthropologist, I was like, that can't be right, because human fatherhood is rare. We are one of only 5% of mammals that have investing fathers, and we're the only ape. Now, for something that rare to evolve, it has to have had a purpose, because it led to amazing anatomical, social upheavals. So that's what I began to do 20 years ago. I started asking those questions. I recruited my first group of 15 first-time fathers when their partners were 3 months pregnant, and off we went.
So the question that's front of mind for me is what is it upstream that made us devalue the role of a father? Well, where did that come from? Because fathers are somewhat seen as surplus to requirement, I think. Where did that come from?
It's cultural. It's entirely cultural, because there are cultures in the world who don't think that. And fathers are very, very integral. So, in fact, one of the most hands-on fathers in the world is from the Aka tribe in the Congo. They keep physical contact with their children for 50% of the day. They carry them around, they co-sleep. Not the mum, they co-sleep. with the child. They are the one that carries the child through the jungle when they're hunting and gathering. They are the one that sings to the child, reads stories to the child. They even, and this is the bit that always gets the headlines, they even will offer a nipple to soothe the child and tell the mother is ready to breastfeed. So it's cultural. We have this idea that, and it partly came very much from the Victorian period, where fathers were seen to be disciplinarians and providing the money, and that was the Victorian idea of being a father. It's also to do with our politics and society for a long time. So women weren't able to go out to work, and that's where we've remained till very, very recently. But there's no biology behind that. That's entirely cultural, and I think also, it's very much the case. Yes, women today, we have contraception, so we can control our production of children. We can earn our own money. We can protect ourselves. We can look after ourselves. So actually, in one sense, you think, well, yeah, what's the dad for? Because I can do all those things which historically the father had to do when women's positions were different. And we've sort of carried on with that, and there's become this mantra of actually then we just don't need them. I mean, I've even been to lectures where they've decided that the Y chromosome is going to become obsolete and that we really won't need dads at all, even to conceive children at some point, and which to me sounds ludicrous. And that's where it's come from. I mean, we've embedded that, and we embedded it in our media. So dads were always bumbling or useless or absent. You know, Daddy Pig is the ultimate bumbling, useless father, and we laughed at it. We think it's funny.
Maybe the way that these two subjects initially do sort of dovetail into each other is when we think about the state of love and the role of men and women. You touched a bit on it there when you talked about how women are earning more and more, so men are becoming a little bit more apparently obsolete in what they can offer to a monogamous relationship. There were some stats that I was looking at before you arrived, and I'll read them out to you. The stats say that only 38% of single women are actively looking to date versus 61% of single men, which is a huge gap. Morgan Stanley projects.
My work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to get done in a list view. Next, I set a priority and a due date to keep things on track. I create custom statuses to organize my progress exactly.
But the reason that you are stuck in life is because you cannot bring yourself to be ordinary. Their life is built on this fantasy. They can accomplish amazing things. And if you're a puer aeternus, you know this. Why do these people exist? Because we're a society of puer aeterni. We're a whole generation of people who are living in our parents' basement. And this is the core of the psychological problem. This is what Jung really discovered, is that they cannot make a commitment, they cannot make a sacrifice, they cannot pay a cost without a guarantee of a gain. And if you cannot do that, you will never move forward in life. Today, we are going to do a lecture on an incredibly fascinating concept called puer aeternus. Okay, so this is something that Carl Jung originally developed, and puer means boy, like a male child, or puella. So I know that I looked at the title of the stream today, and it was like, why some men never grow up. So it actually is a lecture about men and women, but the concept is it's like colloquially known as puer aeternus, but it can be puella aeternus too. Puella means girl, like a female child, and aeternus means eternal. So over 100 years ago, Carl Jung